In the early 1900s, J.J. Thomson proposed that an atom was a uniform sphere of positively charged matter in which electrons were embedded. This model is sometimes called the plum pudding model. Electrons are embedded in a sphere of positive matter, similar to raisins in plum pudding. In 1910, Ernest Rutherford, Hans Geiger, and Ernest Marsden carried out experiments in which very thin foils of metal were used as targets for alpha particles emitted from a radioactive source. Click on what Rutherford expected to observe the results Rutherford expected based on Thomson's model of the atom. Based on Thomson's model, Rutherford expected that the positively charged alpha particles should pass through the uniform sphere of positively charged matter with little or no deflection. Click on actual experimental results to see what actually happens. Rutherford observed that the majority of alpha particles penetrated the foil either undeflected or with only a slight deflection. Every now and then, however, an alpha particle was scattered or deflected at a large angle. In some instances, an alpha particle actually bounced back in the direction from which it had come. This was a most surprising finding, for in Thomson's model, the positive charge of the atom was so diffuse, or spread out, that the positive alpha particles were expected to pass through the foil with very little deflection. Upon making this discovery, Rutherford explained, "It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you." Click on Rutherford's model to see the model of the atom that Rutherford proposed based on his experimental observations. Based on the results of his experiment, Rutherford postulated a nuclear atom. All of the positive charge and most of the mass of the atom is concentrated in a very small volume called the nucleus. Electrons occupy the remaining space of the atom. The radius of an atom is approximately 20,000 times larger than the radius of the nucleus. Most of the positively charged alpha particles pass straight through the diffuse electron clouds of the atoms. Some alpha particles pass close to the small positive nuclei and are deflected at large angles. A few particles score a direct hit on the nuclei and come almost straight back.
Oh, so I'm really hoping that that worked, and I'm hoping that you were able to understand a little bit about Rutherford's experiment. If not, I'll break it down for you now. This is, by the way, lesson 2.3, and you're going to be completing in your notes this section on Rutherford's gold foil experiments. So what Rutherford did, he and Thomson were actually buddies, and he set out to prove that chocolate chip cookie ball model of the atom correct. That an atom is made of this positive goop with negative electrons embedded in it. And so what he did is he took a very, very, very thin sheet of gold foil. That's what you see here in your picture. That's like aluminum foil, but gold and thinner. So it's just a couple of atoms thick of gold foil. And he bombarded that gold foil with what's called alpha particles. Alpha particles are in table O. They are positively charged forms of radiation. Okay? So inside this box is a particle that releases or emits alpha particles, and he fired those alpha particles at the gold foil. And what he thought was if the positive matter of an atom was all spread out, then these positives would just blast through an atom. And most of them did. Most of them passed right through the gold foil. And this is traveling crazy fast. This is traveling at the speed of light, like 3 times 10 to the 8th meters per second. So it has a lot of energy, and he expected it right to just blast through. However, what he noticed was this craziness, that this one didn't pass through, that some were actually deflected. About 1 in 20,000 were deflected back at him. His analogy was great, and I don't know if you caught it. When he recognized this, he said it was about as credible, about as believable as if you held up a piece of tissue paper and I fired, I think he said, a 15-inch shell at you, like with a whatever shoots 15-inch shells, and it hits the tissue paper and bounces back and hits me instead of passing through the tissue paper. It's crazy. It has so much energy, it should just be able to blast through. So what he concluded based on that is he actually concluded two things. Since most pass through, okay, when I say most, I'm referring to the positive alpha particles. They didn't really hit anything significant. He concluded that most of an atom is empty space. Okay, since most pass through, most of an atom is empty space. However, since 1 in 20,000 were deflected, or about, they must have hit something. And indeed, that something must be really, really dense. Otherwise, how would it be able to deflect something moving so fast with so much energy? So it must be super dense. And it must be positively charged. Because otherwise, when the positive hit it, if it were negatively charged, or even neutral. If it were negatively charged, it would have stuck, since opposites attract, but it hit and was pushed away. It was pushed back. So it must be being repelled by this very dense thing. So this very dense thing must have a positive charge. And that very dense thing later became known as the nucleus. And so although Rutherford, it's kind of like a soap opera, although he set out to prove Thomson right, that the positive charge in an atom was all spread out, he actually proved him wrong. The positive charge in an atom is not spread out. It is centered in a very, very small, very, very dense nucleus that has a positive charge. So our model of the atom changed after Rutherford's experiment, okay? And instead of, I guess we'll just draw a picture of it here, instead of it being, you know, that this chocolate chip cookie model with your positive goop and your negative electrons, that was Thomson's model. It became Rutherford's model, which is the nuclear model, where we have a small, dense, positively charged nucleus. So all that spread out charge gets centered in that nucleus with the electrons sort of around it in some kind of cloud. We didn't really know how the electrons were around it, but we knew atoms were neutral. So if they have an area of positive charge, they had to have an area of negative charge. So the thought for the day that I'll leave you with, and it's rather depressing on this Friday, is that since atoms make up everything, and atoms are mostly nothing, they're mostly empty space, absolute emptiness, everything is made of mostly nothing, which is kind of a sad and depressing thought. So on that note, I'll leave you, and we'll talk more about the structure of atoms tomorrow in class. Have a great day, everybody.